All right, so 8.3 is focused on the pH scale. So for the SL level, IB is not like expecting you to have to calculate it, but you will for the HL level. So, you know, you might as well kind of get used to it for right now. But essentially, the equation to calculate pH, it's a logarithmic scale. And so when you're using a calculator, you'll use the log button. Just make sure you use the regular logarithmic button, not the natural log one. So like you don't want the one that has like ln, that's natural log. We want log with a base of 10. So when you're looking at your calculator, you're looking for that button that says log or log 10 on it. Notice that it does have a negative sign added in front of it. So like if you don't type that in the calculator, just make sure you got to put a negative sign in front of your answer. Okay, so it's the negative logarithm of the hydrogen ion concentration. And so because of this, the pH scale is actually an inverse scale because the higher that your hydrogen ion concentration is, the lower your pH will be. And so that's what it means by that the scale is inverse. So high concentrations of hydrogen ions in a solution makes your pH very low. And so that's why we typically say that things that have very low pHs are acidic, because acids have high concentrations of hydrogen ions. That's what makes them an acid, is that they give off or produce hydrogen ions when they're dissolved in water. And so obviously it says conversely, if you have a low concentration of hydrogen ions, that's going to be a high pH value. And what that actually kind of corresponds to is the hydroxide ions. So again, if you have low hydrogen ion, that means your pH is going to be high. And so these are going to be like this over here is going to be acids. This is going to be bases or alkalinity. And so keep in mind that just like hydrogen ions, hydroxide ions are also kind of part of this. And so you can write it in terms of the hydroxide ion concentration. So if they have a low hydroxide ion concentration, they're going to have a low pH, and that's going to be acidic. If they have a high or an increased hydroxide ion, that's going to be your bases. So they're kind of opposites. So usually when we talk about acidity, we talk about it in terms of hydrogen ion concentration because that's what makes something an acid. But just know that on the flip side, bases will have a low hydrogen ion, but they will have a high hydroxide ion concentration, like it says here. Because if something is neutral, that means it has equal hydrogen and hydroxide ion concentrations, which means that all the hydrogen and hydroxides pair up and they make water, and that's why it's neutral. And so if you have more hydrogen ion than you do hydroxide, you're acidic. If you have more hydroxide ions than you do hydrogen, then you're considered basic on the scale. So this is kind of scale how it runs. It runs from 0 to 14. So obviously you can see down here you have high hydrogen ion concentration, low hydroxide ion concentration. So these are the very low pH values. So these are going to be your acids over here. As we go this direction, this side's going to be where we would find the bases because they have low hydrogen ions, but they have high hydroxide ion concentrations. Right here, kind of dead in the center at 7, that's your neutral, has to be exactly 7. If it's 7.01, technically that's basic. If it's 6.99, technically that's acidic. It's not very acidic or basic. It's a very weak acid or a very weak base, but technically it would be not neutral, okay? So on this table down here, it's just asking us to kind of label, would this be acidic, basic, or neutral? And then what would the approximate pH be? So the first one has hydrogen ion equal to hydroxide ion. So which one is that going to be? A, B, or
Neutral?
N? Yeah, that's going to be neutral. Okay, because if they're equal, they're all going to pair up and make water molecules. So it's neutral. And so the pH has to be exactly 7.00. If it is hydrogen ion greater than hydroxide, what's that one going to be?
Acidic?
Yep, that one will be acidic. And so here I would say that it's 0 to 6.99, or some people will just say less than 7. You can write it either way, okay? And then Last one by default, because it has more hydroxide or greater hydroxide than it does hydrogen, that's going to be basic. And then this would be like 7.01 to 14, or you could just say greater than 7. Okay. So that's kind of the generic or the general description of pH and how you tell if something is acidic or basic on the pH scale. But beyond that, you have to sort of understand what happens if you change the pH, what's happening when the pH changes. And so in chemistry terms, every time you move one unit or one step on this pH scale, because it's a logarithmic scale, the amount of hydrogen ion is actually increasing tenfold or decreasing tenfold, depending on which direction you're going. And so that's why it's that log is to the base of 10. Because, for example, if I were to go from a pH of 5 to a pH of 4, like this arrow is showing right here, my pH decreases by 1, but my hydrogen ion concentration increases by 10 times that. Okay, so it increases by 10. So because it's inverse, so it's going to increase instead of the decrease, and it's tenfold. So you have to keep in mind that it's going to be the opposite, and it's going to be 10 times. Okay. So what would happen? What do you think would happen if I went from like a pH of 9 to a pH of 7? What would happen to the hydrogen ion concentration?
It would increase 100 times?
Yes, exactly correct. It would increase 100 times. Every step is times 10. So it's kind of like when we have the metric system, when we go from like deci to centi to milli and everything is times 10, you move the decimal point, okay? Kind of a similar change here in that every time you move one place, your change is times 10 for the hydrogen ion concentration. So on this one that I kind of just drew in here, this would be a times 100 increase for the hydrogen ion concentration, okay? Notice this one up here, because we went from a pH of 9 to 10, so the pH increased by 1. That means that the hydrogen ion concentration will decrease by a factor of 10, okay? Because remember, higher pHs means less hydrogen ion concentration because it's inverse, okay? The bases have more hydroxide and less hydrogen ions, okay? So just keep in mind that, if I move, from 5 to 2, that's 1, 2, 3 times. So that's going to be 1,000 times increase. Okay. So this one, it says black coffee has a pH of 5, toothpaste has a pH of 8. Identify which is more acidic and deduce how many times the hydrogen ion concentration is greater in the more acidic product. So first off, which of the two, because there's kind of two parts to this. So first off, which is more acidic, the black coffee or the toothpaste?
Wouldn't it be the black coffee?
Yes, it would be the black coffee because lower pH is more acidic. Just spell coffee, it's got 2 E's. Black coffee is more acidic. And you could just say that it's because of the lower pH. Lower pH is always the more acidic one. Now, for the second part where they want you to deduce how many times the hydrogen ion concentration is greater in the more acidic product. So now this is where you would have to kind of think about, okay, well, one of them's 8 and the other one's 5. And we just said that the black coffee that's 5, this is the more acidic. So we have to look at how many spaces apart are they? Well, it's 1, 2, it's 3 spaces apart. So how many times more acidic is the black coffee than the toothpaste?
1,000?
Yep. And it's 1,000 times more acidic because they are 3 units of pH apart from each other. And it's that scale is tenfold for the hydrogen ion concentration. So here, there's some practice questions. Some of them are going to ask you to do basic calculations. So for example, it says calculate the pH of a solution. This is the hydrogen ion concentration. So this is where you would literally just plug in your calculator, negative log of 3.2 times 10, you do the E button to the -5th, and that's going to give you your answer. Okay. All right. The last thing is this, what we call the ion product constant, or it's abbreviated KW. So this is going to kind of harken back to topic 7 when we had equilibrium. And if you guys remember, we had like KC, and if there were gases involved, sometimes we had KP. For pressure. C was concentration, P was pressure. So this is just a specific version of that equilibrium constant, okay? It's specifically for water, so that's why it's K with a W there for water. And so basically the generic parts of it are the same, okay? You can see here, this is the equation for water ionizing into hydrogen and hydroxide ions. And you can see that it is a reversible reaction. It's got the double-headed arrow. And so water ionizes, but only very slightly. The equilibrium lies, for this reaction, lies heavily to the left. And so the majority of your substance is going to stay H2O. Very little of it's actually going to be the H plus and the OH minus, okay? And so the KW value for water is this value when it's at this temperature. And so because we know it's that value, we can actually use it to help us do calculations. All these equations are kind of related, okay? So like I could say, you know, KW is this. And so if I know the hydrogen ion concentration and I know the hydroxide ion concentration, if I multiply them for any substance, it's always going to equal this number. And so if I know one of the two concentrations, I can solve for the other one because I know that KW is always 1 times 10 to the negative 14. So what I'm going to do really quick, I'm just trying to find some more space. I'm going to write it, I guess I'll do it right here. I'm going to kind of write a quick summary of these equations for calculating pH and KW and all that stuff, because all of them are kind of related, okay? So for pH is the negative log, oops, there's an O in there, the negative log of your hydrogen ion concentration, okay? You can actually solve for the same thing for hydroxide ion. It's just, instead of pH, it's called POH. And it's the exact same equation, the negative log, but instead of the hydrogen ion concentration, you use the hydroxide ion concentration. So the equation is exactly the same. It's just one of them, we're using the hydrogen ion concentration to solve for pH, which is most commonly what you have to do, since pH is how we measure acidity. But if you need to, sometimes you might be given a hydroxide ion and you have to calculate POH, okay? Now, pH and POH are related because anytime you add the pH of a solution and the POH of a solution, it always equals 14 because that's our pH scale. It goes 0 to 14. So the pH and the POH, they always have to equal 14. Now, the inverse equations, if I go back up here to the first page, okay? So here, this was the inverse equation right here. So if I want to calculate the hydrogen ion concentration and they give me the pH, I just do 10 raised to the negative pH. That's the inverse or the opposite of the pH equation. So let me switch back to purple. So if I want to do the hydrogen ion concentration, I do 10 raised to the negative whatever my pH value is. So these two, they're just opposites of each other. It would be like if I did, you know, if I wanted to add and I said, well, what's the opposite of adding? And it would be subtracting. Or if I said multiplying and the opposite's dividing. It's the same thing. We're doing the logarithm. The opposite is doing 10 raised to the power, okay? So I can do the same thing for POH, okay? If I want to calculate the hydroxide ion concentration, what do you guys think it's going to look like based on what we just wrote for the other one?
Ten to the negative POH.
Exactly. Okay. So because it's the inverse, so it's still the same setup for the formula. It's just we replaced hydrogen with hydroxide ions. Okay. But the same thing, 10 raised to the negative POH in this case. Now, the last thing is this KW equation. This KW equation, it goes in there too, because KW is always 1 times 10 to the negative 14. And so I can say 1 times 10 to the negative 14, which is KW, is the hydrogen ion concentration times the hydroxide ion concentration. So with this, and you'll never actually solve it this way, you'll always have to do, like you'll either do 1 times 10 to the negative 14 divided by your hydrogen ion concentration, and that'll give you the hydroxide ion concentration. Or you could flip it the other way and you could do 1 times 10 to the negative 14 divided by my hydroxide ion concentration, and that's going to give me the hydrogen ion. So you can rearrange it either way depending on what you need to solve for. So all of these 6 equations, okay, the purple, 2 in purple, the 2 in red, and then the 2 in blue, and I know the last one in blue I kind of rewrote it a couple different ways, but it's still the same equation. These are all sort of interconnected. So depending on what you're given in a question, you can like use any of these. You know, if they give you the hydrogen ion concentration, they ask for pH, you know, that's really easy. Use this one. If they give you the pH and they ask for hydrogen ion concentration, you can use this one, okay? There might be something where they like give you the hydrogen ion concentration, but they ask you for the POH, okay? In that case, you're gonna have to use 2 equations. What you would do is you would first use this one, where I can use the hydrogen ion concentration to solve for the pH, and then I can plug the pH into this equation and do 14 minus the pH. That'll give me the POH. Or I could use the KW equation. If they give me the hydrogen ion concentration, I can use this one right here. I can do 1 times 10 to the negative 14th divided by that hydrogen ion concentration, and that should give me the hydroxide ion concentration. So there's multiple ways that you can sort of apply these equations, as long as you sort of understand what information they're giving you and use the correct formula or combination of formulas in order to solve for whatever they're asking you for, okay? And so that's kind of like on this number 2, this table, that's kind of what you're gonna do. So they've given me the hydrogen ion and they want the hydroxide ion and the pH. So you could use the KW equation, which is like this one right here. You could use these to solve for the other concentration. Okay, so like for example, on this first one, they give me the hydrogen ion concentration, so I could use this one over here and solve for the hydroxide ion concentration. For the second one, they give me the hydroxide ion, so I could use this one on the left and solve for hydrogen ion. So you could use that one to fill in there. Now to get pH, there's again multiple ways you can do it. The easiest is once you know the hydrogen ion, just do negative log of that. So for the first and the third one, you can solve for pH directly from what you're given. But for the second and the fourth one, you're going to have to use the hydroxide ion first to find hydrogen ion. And then once you know the hydrogen ion, then you can do the pH, okay? Then once you have all the pHs, then you can do the last column. You can't do the last column until you know the pH, okay? Because that's our pH scale. One thing I will say when you're talking about like sig figs with these, if you notice all the concentrations here on this table have 2 sig figs. So whatever number of sig figs your concentration has, your pH should have the same number of decimal places. So since all of the concentrations on this table that they gave us have 2 sig figs, that means all of our pHs should go to the 100th place. Okay, they should have 2 decimals. That's the general rule for when you're rounding and talking about pHs versus concentration. So you look at how many sig figs the concentration has, and that's the number of decimal places that your pH should have. And then backwards, same thing. If you know the pH and your pH has 1 decimal place, that means when you solve for your concentration, you're only going to give it 1 sig fig, so it's going to be a whole number. Okay. And that's basically it for today. Most of your practice questions have to do with sort of applying some of those formulas and calculating things. There's a couple where you're going to be answering things about, you know, pH scale or acidic basic, but mostly you're kind of applying those different equations and solving for the different values.